All right, good morning, everyone. We're going to go ahead and get started on this second day of the I2B2 Transmart Symposium. So if I can have your attention, please, we will get going. I've got a couple of logistical notes that I'd like to make as we welcome you into the second day. The second day is going to be a bit smaller, a bit more casual, and a bit more interactive. So we do have some prerequisites for the second session that you might want to take a look at. It takes maybe, 10 or 15 minutes to get set up. You're going to get a lot more out of that session by taking care of those prerequisites if you can. We will have folks available to help as well. And then the third session of the day will also be interactive without any prerequisites. So just wanted to make that clear up front. For anybody who is, going to give a little note to my presenters here, for folks who are presenting and they're going to be using their own machines, you'll come up here, you'll connect the HDMI cable, we'll go through some steps to kind of share your application so that we get things looking right on the PowerPoint and on the screen in the room here, on the Zoom in the screen in the room here. But please do join the Zoom beforehand. You're going to present kind of as though this is just a sort of two-screen setup like you might at home or at the office, and see if you can turn off your audio and microphone. So getting that so we're not getting any sort of feedback or audio issues as you go ahead and connect. And I'll ask for grace and space in advance if we do run into any AV issues as we get going and as we transition between presenters. We will figure it out, but just bear with us. So let's get started. If I can have Griffin, maybe you want to kick off your first session. So welcome, Griffin.
Thank you, Mark, and for everyone who returned today. All right, so our first workshop today is going to be about machine learning and I2B2 to address EHR data quality issues. So we started this a little bit yesterday. I gave a presentation on the computed phenotype pipeline. That talk was much more focused on the methods in federated learning. Today, I'm going to dive more into implementation in the I2B2 platform for computed phenotypes. Another thing that's related to computed phenotypes is completeness of data. And then Jeff Clan will be here in a little bit, and he'll talk about some machine learning methods we use in I2B2 to find patients who have sufficient data in the EHR to be able to do things like computed phenotypes and other types of analyses. And then Jackie Honorlaw from the VA will be talking about a system called CIPHER. That's not directly related to I2B2, but it's showing other use cases for computed phenotypes and some visualizations and methods. And it may be a peek at some of the future things that we may be able to do with computed phenotypes inside of I2B2. These are all related to issues that we have with data incompleteness and incorrect diagnosis codes in the electronic health record and machine learning methods to address that. So first is computed phenotypes. And my disclosures, this talk will be similar to the one I gave yesterday. So you'll see some overlaps. Some of the slides are swapped out with other slides that are more specific to how this is implemented in I2B2, what scripts you have to run, how you actually get this to work. So as I mentioned yesterday, physicians have to assign diagnosis codes for billing purposes, even when they're testing to see if a patient has a condition. So a lot of times, across many different diagnosis codes, only half of the patients who have that code end up really testing positive for the condition and have the medical condition, but that code remains. So the electronic health records are filled with these incorrect diagnosis codes, and they can result in misleading findings when you run queries. For clinical trials, it means that trial investigators may think that there's a certain number of patients at the hospital, but it turns out maybe only half of those patients are really eligible, and they may fail to reach the enrollment targets of the study. Then this was a study they did at Vanderbilt, where they did manual chart review to figure out what conditions patients really have after reading the physician note and comparing that to the billing codes. When a patient has a single code for a diagnosis, on average across these diseases, only 37% of those patients actually have the condition. Just a positive predictive value or precision of those diagnosis codes, where a single code is pretty low. In fact, it's more likely that the patient does not have the condition. Once you look for patients who have one or more codes, so anyone just has some code, it goes up a little bit because when patients really have a condition and they're being treated multiple times for that condition, so you end up with more than one code. For patients who have at least two codes for condition, the positive predictive value went up to 84%. But by just looking for patients who have a bunch of codes in the chart, you're going to be biasing for sicker patients or other factors that you may not be aware of. It also varies a lot by condition. So for example, for breast cancer, a single code had a very low positive predictive value, around 10%, but other things like AFib or gout, that was about 50%. Still not great, but quite a bit higher than other codes. And as I'll show later when looking at my own institution, there's this variability as well, where the EHR is not consistent across different diagnoses. Some diagnoses codes work really well, others are terrible, and there's different approaches to addressing the data quality issues depending on the disease. So to address this, we use computed medical conditions. On the left is what happens if you use a raw diagnosis code. You have low precision, so the patients who you think have the diagnosis are different than the ones who really do. Then there are rule-based phenotypes. This is when you bring together a group of clinical experts, and they set some workflow. So I'm looking for patients who've been coded twice with type 2 diabetes, never for type 1 diabetes. If you had an elevated A1C and other criteria to finally make a yes/no decision on that condition. It takes a lot of time and effort and cost to develop these. When there's a new medication that comes around, you have to come back and change that workflow, and it may not work at a different institution. What we're looking at in ITB2 are probabilistic phenotypes. These are algorithms that can look at the EHR data and without any additional input can automatically build a model that predicts the likelihood that a patient has a condition. The big question, since we did a lot about LLMs yesterday morning, why can't we just have an LLM go through the entire EHR and clean everything up? The problem is that the computed phenotypes are very scalable and cheap, and we can run these across millions of patients and billions of data points. LLMs are getting more and more efficient, but they still have a high cost of computation, and they're good for things on the scale of maybe thousands of patients, but not millions of patients and billion nodes. So they're slow compared to what we can do with computed phenotypes. Also, some trials have complex eligibility criteria that may combine many phenotypes in complicated ways. They're looking for dates or sequences of events, and some of these things are just challenging for LLMs to do, whereas more traditional machine learning models may actually be better in certain circumstances. There's also with LLMs uncertain performance on low prevalence diseases. These computed phenotypes are designed so you can run them across millions of patients and find the 1,000 that have the rare condition. The LLMs may not work as well when you're looking for those unusual cases. And there's general LLM concerns like hallucinations, ethical issues, and the stuff about values that Zach and others were talking about yesterday. So there's a set of innovations that kind of built up over the last 15 years that lead to the algorithms we're using in ITB2 today. So the first thing is something called fee codes. What this was back in Vanderbilt again in 2010. There are many different codes, billing codes for a medical condition that are important for billing purposes, but for researchers, they just want to know, does the patient have diabetes? So fee codes group related diagnosis codes for a medical condition. So there's a couple thousand or so of these fee codes, and they take the tens of thousands of ICD-9 and 10 codes and group them together. So this is our starting point. We're not building computed phenotypes for individual diagnosis codes. We're building the phenotypes at the disease level, at that fee code level. Then in 2008, this is sort of the real key paper in this. It's about an algorithm called Phenorm. And the insight here is that, before I was saying patients who had more occurrences or recordings of a diagnosis in their chart may be more likely to have that condition. But in Phenorm, it shows that it also has to be normalized by healthcare utilization. So if a patient has been to your hospital 3 times, and all 3 times was to see an endocrinologist about diabetes, they're probably at your hospital for be treated for diabetes. If they've been to your hospital 100 times and only 3 of those visits ever mention anything about diabetes, maybe they don't really have diabetes and that was a test or an incorrect code that was entered. So there's this context of how much have they been to the hospital, what are the other things they've been to the hospital for, and does that align with the fact that a patient may have the medical condition that you're interested in? So by normalizing by this healthcare utilization, you can come up with a score. And when you plot the distribution of scores for patients, you get this kind of curve that has 2 bumps in it. And like the blue bump on the left, those are the patients who don't have the condition. They got the code once because they got tested or some random errors. The curve on the right, the red curve, those are patients who are being seen lots of times at the institution for the condition relative to healthcare utilization. And for many conditions, it separates out like that, those 2 curves, and you can find that point in the middle and separate it out to 2 populations of patients who really have the condition and the ones who don't. So we, at Mass General, Brigham, and other institutions, we started using that back in 2018, and then in 2019 and 21, further advancements to that algorithm were made. The first one is called CIPHER. So Phenorm is only using the diagnosis codes for a condition plus the number of visits, basically, that the patient had. In CIPHER, it's using something called embedding regression, where it's using similar techniques to large language models, but in a different way, to find additional features in a patient's chart that may be relevant to the condition that you're looking for. So it looks at the entire electronic health record at co-occurrences. So how often do different features in the EHR co-occur with the diagnosis of diabetes within a 30-day window? So look at how many patients have insulin and diabetes within 30 days, how many patients have cancer and diabetes within 30 days? How many patients have an A1C and within 30 days of diabetes? So counts all these different numbers, and for every different condition and code inside of the EHR, and creates this big matrix of co-occurrences. And then the embedding regression finds for each phenotype a set of features that are related to it. This in its own isn't a model. It's just a list of 200 or so items related to each condition. And you can do different things with it. You can, I think we'll see later, knowledge graphs and visualizations. We're using it as a feature selection tool to go from the million different concepts in the ITB2 ontology down to a few hundred things that we can build a statistical model on. So it doesn't rely on the clinical experts. It's just using the data to tell you what's related to a condition, as opposed to the more traditional way of doing this, where you have to find an expert in every one of the diseases that you want to build a model for to figure this stuff out. There's some tuning in CIPHER, so it's optimized for those phe code groupings of diagnosis codes, RX norm medication ingredients, LOINC at the biomarker level, and CCS procedures. When we have this in I2B2, we have some mappings that will go from the ACT ontology, which a lot of people use, to these roll-ups and coding systems. So for example, at Beth Israel, my raw data are in CPT diagnosis, CPT procedure codes, and we use this mapping to go to the CCS. You can extend this in any way you want. It's not limited here. It's just there's certain things that the algorithm does to account for frequencies that are tuned for these different domains. COMAP will then take the feature list from CIPHER, combine that with Phenorm, and build you a model that incorporates both the number of times the patient's been seen for a condition, the total amount of healthcare utilization, as well as those 200 other features to give you an even more accurate model for that condition. It's very scalable, and I2B2 is doing this all at the same time. So you're not building a model for diabetes and coming back and building a model for hypertension. And it creates a one co-occurrence matrix, extracts all the features, and then in a very efficient way is building you 1,000 different computed phenotype models, one for every condition that you have at your institution. Another aspect of this is removing patients with low utilization. When a patient has only been at your hospital once, there just isn't enough information to create a reliable phenotype. You don't know if they're at your hospital that one time to get tested for the disease, or if they were there for a consult or what. So in order to really do this, you need a certain amount of data in the chart to be able to build a model. There's simple and complex ways of doing this. The method I'm using at Beth Israel or my hospital for the phenotyping is I'm just looking at patients who have 3 visits since 2010. We have data that goes all the way back to 1997, but it's not fully complete. Like we have diagnosis codes that go back to 1997, but vital signs only started around 2010. And if you have sort of partial incomplete data, the models get confused on that and don't work as well. So you usually start at the point in time when your hospital began collecting complete data across lots of different domains that you may need for your models. Jeff will be here in a little while, and we'll talk about a machine learning method, which is a much more sophisticated way of finding patients who are likely receiving most of their care at your institution and therefore have more complete data than patients who are really getting care at another institution and maybe stop by your emergency room a couple times, and that's all the information you have about them. So this is what it looks like when you run the Kessler algorithm. So I create a co-occurrence matrix at Beth Israel Lahey. I run it through Kessler, and it says these are a set of features that are related to type 2 diabetes. A lot of them make sense. There are medications here that type 2 diabetes patients would take. There's things like type 1 diabetes that's over here. And it doesn't mean that if a patient has type 1 diabetes in the chart, it's evidence that they have type 2 diabetes. It may just mean that sometimes when physicians are coding or testing a patient for type 2 diabetes, type 1 gets in there. So it's not, these things aren't all evidence for a condition. They're just things that happen to appear in a lot of patients' charts who have that condition. So it's a feature list. It's not a model or evidence for or against a condition. What COMAP does is then takes the list of features on the left and the actual data about your patients and builds a model to predict which patients have that condition. So it assigns weights to those features. Again, you don't need to have a gold standard or chart review. This is all an automated way. It's just looking at the distribution of patients you have and trying to cluster them into 2 cohorts. And one of them would be the cohort that has the condition, the others that don't, and it's putting weights here to separate out those 2 populations. So it gives me like a positive weight for type 2 diabetes, meaning the more visits the patient has coded type 2 diabetes, the score goes up. The utilization, so the more total visits the patient has, the score goes down. Metformin boosts the score up a little bit. High BMI boosts it down a little bit. So you plug in all these different things for the patients, and you get a score. The first graph here is a distribution of all the patients at Beth Israel and what their score is for this type 2 diabetes model. And you see those 2 bumps. And there's a method where you fit 2 Gaussian curves to it. So the dashed blue curve and the orange curve, those end up being the best location and sizes of curves that will fit the distribution I had. And then the model finds the point where those 2 curves cross, and that's your threshold. And then all the patients who had a score above the threshold, the model says has diabetes, and the ones below that threshold says doesn't. That default threshold works pretty well. What you really want to do if you have the resources for it is to take a small number of patients, maybe 20 patients, do some chart review and manually determine if you think they have that condition or not. And then based on that, you can look up where they are on that curve and find a better point to build that threshold. So I'll show a little bit later what you get with the default threshold, and then with a little bit of chart review, you can optimize that threshold based on whether or not you want to find more patients or increase the positive predictive value or tune it the way you want. Without any chart review at all, it's just doing this basic default way of generating that score distribution and telling you the cutoff. So when you put it together, the first step inside of I2B2, it creates this big co-occurrence matrix and then uses Kessler and embedding regression to find a set of features, about 200 or so features, for thousands of different medical conditions. And that creates a knowledge graph. It doesn't actually draw out that knowledge graph for you, but it's a database table for which has kind of two columns, the condition that you're interested in and all the features that might be relevant. Then the COMAP algorithm then takes that list of features, all the data that you have about patients, and then assigns those weights. And then the third step is you take that model and you run it against the millions of patients in your database, and it'll give you a list of phenotypes that it thinks every one of your patients has, and these get entered into I2B2 as derived facts that then investigators can then use in their queries instead of the raw diagnosis codes. Are there any questions so far? This is the workshop, so you can interrupt me as opposed to, yes, sir. Yes.
Using computed phenotype, so I think maybe there are some possibilities. So firstly, you just give an example, the type 1 and type 2 diabetes. So can we also discover the subtypes of diseases and how to mitigate the heterogeneity of diseases, like a type 1.5 diabetes?
Right, so in the example here, I'm taking phe codes as a starting point. So phe codes has defined 2,000 things that it calls the set of medical conditions that you're interested in PheWAS studies. So here I'm only building models based on that set of 2,000 medical conditions. But you can use these same algorithms to create a phenotype model for anything else. Sometimes it's hard. You might have to start with some gold standard. So we did this in things like long COVID or other conditions where if you're a clinical trial and you're looking for patients with some condition that's not coded well with ICD-9 or 10, if you have a list of patients who you know has that condition, you can use this model, this algorithm, to find additional patients that are similar to that. So yes, you can do that kind of subtyping or find models for things that are not coded today in ICD-9 or 10. Those things, though, you usually need to start with some list of patients who you can flag in some way as a gold standard to build a model around it.
The second, that you show distribution, two Gaussian distribution together. And if we can look at the Gaussian peak in fine high resolution, maybe we can find small peaks. So that may be the subtypes of new disease.
Perhaps. Unfortunately, Tangxi isn't here, so the statisticians can tell you much more about that. I don't know if that would be the best way of finding the subtypes. I'm seeing the statisticians that I kind of know here going kind of a little bit like this, but what I have done, though, is I've ordered patients by where they fit on that score and chart other things like what is the hypertension rate of patients across that score level. And you get some weird bumps across those things, and that might show you some interesting things to think about. It's a really, I think, interesting point of how to do the subtypes. Yeah, I'm more on how we actually run this here, but I think there's a whole bunch of stuff we can do at another time on the actual algorithms and exploring those in depth. Are you anyone here burning with comments that you want to say about that?
Oh, no, I was just want to say. For example, the way we code in our EHR system is not that well coded. So like when in the feature selection set in the CIPHER, in the network, when you feed in, it's not a good separation of them, but it's very specific to the system. And that is why when you run COMAP or MAP, you actually have to run it specific to the cohort and the system itself. And the distribution will look different depending on the cohort and the training data set you have.
Great. I'm going to mention a little bit later, but one thing that's really important
Griffin?
about this.
We got.
Oh, great.
Do you see any dependence between the institutions and the models, or might you get a better performance out of the algorithms if you took that into account.
Yeah, I mean, absolutely. This is, we touched on this a little bit yesterday about how when you're doing this only within your institution, you can overfit to unique medications or treatment options or diagnosis tests there. And as those things change, the models can fall apart very quickly. And they may not translate to other institutions. But an advantage of these algorithms is they can work in a federated learning method so that if you have some other partnering hospitals, you can exchange summary statistics, no patient level data, and you can build a more robust model that isn't overfit to any one site. So there is that risk. We do see that the same model will pick out different features at different institutions, but if you look across institutions, you get stabler sets of features that end up working better.
Does that say that a model built at an institution is overfit? Perhaps one should train at each institution. You know, there's two ways.
You're going to want to train this at your institution, but it could overfit, and you have to retrain the model multiple times over time because as things change within your institution, the accuracy will decrease. But again, the advantage of these algorithms is that they're designed to work in a federated learning method so that you do have that ability to collaborate with other institutions and build a base model that's more robust that then you can tune for your local site. And what I want to kind of point out is that usually in I2B2 for 20 years, when we have a new feature in I2B2, it's just install this software and here's the feature. This is a little bit different. This is machine learning, and you don't know exactly what you're going to get when you run these. And the model might work great at your institution. The data that you have might make it so these models don't converge. There are scalability issues with these things, data completeness components to it. So this is a little bit of a different install and use system than what we normally have done inside of I2B2. Institutions that try this for the first time will almost always run into some kind of problems where we have to look at their data, figure out if the mappings are correct, tune things a little bit to get stuff to work. So once we're going from standard software to actual machine learning and AI, things get more complicated. And I think there's a little bit of a reason why LLMs, we've seen all the great things about them, but they're not yet into I2B2, just because of the challenges of working with these things that aren't always deterministic or predictable when you install it at a new institution. Right, this is a plot I made that helps me think about some of the different approaches to computed phenotypes. So on the x-axis here, this is the number of times a patient has been seen at my institution for type 2 diabetes, and it's the log of it plus 1. And then the vertical axis is the total number of hospital visits, and log again of it, so the healthcare utilization. And plotting patients who are coded with type 2 diabetes, and they form a cloud. And the vertical green line, this is the really simple, I'm looking for patients who have more than 2 occurrences of that on a chart. And that's equivalent to creating a vertical line at looking for patients who have 2 or more visits for diabetes without any consideration to their healthcare utilization. The horizontal red line, this is that removing patients with low utilization. So here, before even doing any kind of phenotyping, I'm removing the patients that had 1 or 2 visits and just this may not be enough to do anything. So that's looking at utilization, but nothing related to the diagnosis that I'm interested in. The purple line, that's phenorm. So that's finding a best fit line that takes into account that ratio between the amount of diagnosis codes for the condition compared to the healthcare utilization, and everything to the right of that curve, phenorm would say is diabetes patient, everything to the left, it says it is not. And then the COMAP and Kessler algorithms add a little bit of extra to it, the features further down on that table, and that will take it looks very similar to phenorm, but in certain cases, it will pull some patients to one side or the other side. So I have the orange and blue dots kind of representing where COMAP would either say, yes, the patient had the condition or not. And I like this graph because it helps me think about those different algorithms and the evolution of it, where in ITB2 20 years ago, we had the green line, and then in 2018, it's the purple line, and then now it's a bit more complicated, and there's some nuances with patients that give you those two different clouds at this point. So after you have a list of patients and their scores and the thresholds, you have to get this into I2B2 so investigators can use it. And I don't think we've solved this yet, or the training yet on how to explain computed phenotypes to investigators. So this is how we have it loaded in today at Beth Israel. And it's a starting point. I think there's more work that has to be done to help people understand when to use phenotypes, when to use the raw diagnosis codes, what the trade-offs are on them. So we have a folder in the ACT ontology called diagnoses, and here you can get the raw IC9 and IC10 diagnosis codes. And if you want to maximize your recall, so find every patient who's been coded with it, and you're willing to kind of just sit down and do the manual chart review, those codes might be best. The under a research phenotyping folder, this already exists in the ACT ontology, there's a folder called phe codes. That's the phe code grouping. So there's no probabilistic models, Kessler, COMAP. This is just the 2010 roll-ups of raw diagnosis codes into those 2,000 or so diagnosis code groupings. So here, this is, you want as many patients as possible, but you don't want to have to hunt around for all the different diabetes codes. You can drag the one phe code folder for diabetes and get that. But then we add two additional flavors of phe code folders to the ACT ontology. One is something called phe codes probabilistic not validated. So the algorithms run Kessler and COMAP and I2B2. They're unsupervised models, meaning no one is checking them. It just, you press the button, it runs for a few days, and then it generates these millions of facts for the patients. And no one really checks it. However, when we've done this at multiple hospitals, in general, these work better than the raw diagnosis codes. So I put in the phe codes for about 1,000 different medical conditions at Beth Israel, and I try to explain to investigators, I don't really know the accuracy of those models, but from other institutions, the vast majority of these models work a lot better than the raw diagnosis codes. So if you're running a clinical trial, you're getting low yield, meaning a lot of patients you're pulling out don't really have the condition, you can try using these computed phenotypes, and you'll probably get better results than you were getting before, but I just don't know how much better it is, and in some rare cases, it may be worse. But in most cases, it's better than nothing, so you have it there. Then we do manual review on sort of high priority conditions. Manual review means paying nurses to go through charts and come up with about 20 patients per phenotype where I can use to tune the models and come up with accuracy scores. We've done that for a few dozen conditions at Beth Israel, and then I put those in a separate folder. So these are the ones that have been validated, and I can give people real positive predictive value and recall measures, and they can use those. Those would be the best ones to use in a study. But again, I only have about, I think it's 20 or so in there because it costs money and time to build that out. I will never do chart review at Beth Israel, humans doing chart review for 1,000 different medical conditions. Maybe LLMs will be able to help with that at some point. But today we have these different choices for investigators of raw codes grouped into phe codes, the not validated models, and then the validated models. And then the validated would be best, but when you don't have that, you kind of make a decision on whether or not you want to use the raw codes or the unvalidated based on whether you're trying to find more patients or have better yield when you're pulling those patients out. Then I also have a concept which is called base cohorts. So that was just that starting list of patients who have a minimal number of visits for the model. And you can use that somewhat for negative conditions. So if I'm looking for patients who have a phenotype for asthma, that's finding patients who have asthma. But what if I want to find patients who don't have asthma? If I just say not the phenotype, then You're also getting these patients who had one visit who you couldn't determine whether or not they had it. So you would say, I'm looking for patients who are in the base cohort, but even though they were in the base cohort, they didn't have that phenotype. So then you can infer that they don't have that medical condition. And I think Jeff will talk more about the loyalty cohorts and kind of better ways of doing it than the simple 3 diagnosis dates that I use at Beth Israel. And then all the code for this, Kessler and COMAP are a combination of database code in SQL as well as R scripts. I'll talk a little bit more about that. It's included in starting in ITB 2.1.8.1. The SQL is for SQL Server and Oracle. And this is new. We're rolling it out to institutions. Each institution will run into some kind of a problem. As we find out these problems, we improve the documentation and the code to make it easier and easier for sites. I don't think we'll ever get to a point where people just push a button and then all of a sudden it's done. There's always going to be nuances in your institution's data which require some tuning or some looking into some of the details of the algorithms. This is the chart review results at Beth Israel. Across, it's 19 I'm showing here, conditions. For patients who have one diagnosis code in their chart, the mean positive predictive value is 0.57, so about half of these patients don't really have the medical condition. If you're looking for patients who have 2 or more occurrences of a condition, you get all the way up to 79% precision. So much better, but again, you've lost a lot of patients and you may be biasing these in some unusual ways. Using the Kessler COMAP with that default threshold on the score bumps your positive predictive value up to 87%. So now we're doing pretty good. And then for after you've done the manual chart review, I'm trying to target a positive predictive value of at least 90% so that the patients you're querying, you're pretty confident they have that condition. So I can tune that up and get a positive predictive value of 90% or greater for all these different conditions. The big question is, though, what kind of recall you get when you do that. And the majority of the computed phenotypes end up with pretty good recall. More than half the patients remain there. And there are other smaller number of conditions where the phenotype algorithms work. They build a model, and you can get the patients who have the condition, but the recall is lower. And for these, you can handle in different ways. You can change your threshold. So maybe you're willing to have a lower precision, but increase the recall. And it might depend on the use case of the investigator. I do want to point out again that not all conditions are the same. For prostate cancer at Beth Israel, a single code works great. You don't have to do anything. Just have the point to people to the raw diagnosis code, and pretty much everyone who has the code is going to have that condition. Breast cancer is interesting. Have patients with a single code for breast cancer, 90% of them don't have breast cancer. But if you look for patients with 2 diagnosis codes, nearly all of them do. So think, I don't know why breast cancer and prostate cancer are so different. It's how it's billed or how mammograms or other tests are done within the institutions. But I wouldn't know that ahead of time. You need that chart review to know that this is how these codes are used at this institution. Very few conditions you can use the raw diagnosis codes and work so well like this. The majority of conditions, the phenotypes work much better than the raw code. And then for the majority of phenotypes, they work a lot better with both good positive predictive value and recall. The right-hand side, I had 2 nurses review all the charts to look at inter-rater agreement. For those diagnosis codes that work really well, there was good agreement between the nurses. Down at the bottom, the ones where the phenotypes, they had the low recall, a lot of times the nurses didn't agree. It's not only hard for machine learning algorithms to do this, it's hard for humans to make some decisions sometimes on whether or not a patient has a condition or not. I spoke to them after the completion of it, and it is like that. When a patient is a couple codes and some other things, it's really difficult sometimes to know this. So when it's looking like there's low accuracy of the phenotypes, what are you comparing against? And sometimes you have to compare it against the humans are doing. These are nurses from the clinical research center. So these are the people who actually read these charts to find patients to recruit for studies. And you know, the machine learning models, can they do similar kind of work or better at a more efficient and cheaper way? This is the result of Beth Israel. This is a set of about 70 computer phenotypes were validated with high positive predictive value at another institution, showing that it's not one site. We've done this at many different sites. And again, the majority of phenotypes, when you do the manual chart review, end up working really well, despite the simplicity of it. And again, you can do this in a federated learning method where the summary statistics that are parts of the steps of these algorithms can be shared across institutions for better results. Some quick implementation details. This is a schematic of the I2B2 CRC cell where the patient data are stored. At the top, that's the standard star schema and the query tool tables, the QT tables. The new digital twin stuff, digital twins are what we call the combination of computed phenotypes and the loyalty cohort part. That adds a number of new stored procedures and tables. There's mapping files you have to load in to map to phe codes and to CCS procedures. And then outside of I2B2, you have R and R scripts that do the embedding regression and the COMAP models. So this is adding a lot of new components to your I2B2 instance, including R, which you probably didn't have before. So again, it's not install a new I2B2 like you've normally done it and it's there. There's a bunch of new stuff that you have to do that you haven't done before in a typical I2B2 and ETL. This is kind of a list of the different steps. Most of the computation is happening in the database. It's the vast majority of the time is spent constructing that big co-occurrence table, and then in COMAP there's a big covariance table. So these are done with stored procedures. You run these, come back the next day, and they'll be finished. Then the result, those aggregate tables, the co-occurrence table and the covariance table, you pull out of the database and send to R. R does the final analysis on it and then sends the result back to the database. You can do that in either two ways. You can either have the R scripts directly querying the database, or you can export the database tables as CSV files and load those into R. And it depends on whether the environment you have R on has connectivity to the database or if it's separate networks and you have to completely disconnect R from your live I2B2 database. The R scripts support either way. It shows you code in there, comments on how to either do a direct connection to the database or work through files that you're passing back and forth. But there's 3 points in this pipeline where you have to do R scripts and pull data from your database to the R script and then send the result back to the database. And then finally, you'll get the slides here. I'm just kind of putting it all here in a very dense way so you have all of it. There's on the community website, there's a wiki page that describes, as a starting point for these digital twin technologies. There's specific documentation for the computed phenotypes that goes over the content I talked about today with some additional steps on how you walk through the different scripts. Then in the I2B2 GitHub and the code, there are the different files you're going to run. The first one here is a SQL script that creates a set of tables and stored procedures in either in SQL Server or Oracle. Then the next three, then there's the mapping file load in, and then a couple SQL scripts to process the data for Kessler. So this is mapping your local codes to the phe codes and to CCS procedures, RxNorm medications, and LOINC laboratory tests. Then the Kessler prepared data script generates that big co-occurrence table. Then the R scripts run the Kessler algorithms, the generating embeddings is called, and then embedding regression. And the result of that are the list of features for each of the phenotypes that get loaded back into the database. Then the database will generate the covariance matrix for COMAP. There's a COMAP R script, and then final set of database scripts that will generate the derived facts for the patients, then add those computed phenotypes to your I2B2 ontology. And I'm not going to go into details here. The documentation talks in more detail what each of those files do. It walks you through the steps. There's a lot of comments in these files on how these things work and how to tune it. By default, these sets of scripts are only generating 3 phenotypes. I think it's like diabetes, hypertension, and rheumatoid arthritis. And that's just to make sure you have the whole workflow in place and make sure it runs quickly. Then you want to uncomment a part in those scripts to allow it to go through, instead of 3 phenotypes, do it for every condition that you have in your EHR. And try it out. Again, you're probably going to run into problems, but you can contact me or the foundation. We'll connect you with the right people and meet with you and help you out going through this. And if you can get through the process at your institution and generate the computed phenotypes, we're looking for sites who want to work together in that federated learning model so that we can build robust phenotype models across different I2B2 institutions. So that was the end of what I had. Is Jeff here? Yeah, so any questions for me before we switch over to loyalty cohorts? Maybe we have time. I know we're getting a little bit close to time here. How are we doing on it? Yeah. Okay, so let's do a couple questions. You can do an online question. I want to make sure that we have time for the other 2 speakers. What is the reason patients hadn't been seen for the condition? Is insurance, demographics? Right, a patient may be coded for a medical condition but not have that condition. One reason is because they're being tested for that condition, or and they didn't really have it. Other times it's just incorrect codes that were added to it. Patients receive care at multiple institutions, so a patient may be somewhere else getting their care for that disease, and you don't see a code for it at your institution, so it may appear like missing data. It's a complicated question, and it's a little bit out of scope to go into why it is, but the point is there's a lot of messiness in the coding of electronic health records, and computed phenotypes will help you remove the patients who are incorrectly coded for something, but it doesn't by itself help you find the patients who are missing the diagnosis code.
If you want to take another question, do you want to use this mic and I'll get Jeff set up?
Yes. How does this methodology perform when a diagnosis is based on the results of a procedure, non-numeric test result, or imaging data? There's an out-of-the-box algorithm that we have, which is very simplistic. Again, it's looking for patients with diagnosis codes related to the phe code and features it can pull out of it. There's much more stuff you can do with these 2 algorithms. For example, you can use natural language processing to do an initial feature extraction from their nodes. And these can be additional features that are pulled into the models. You can use large language models to analyze images or other signal data to extract features that can be pulled into this as well. So you're not limited to what I'm showing. This is how we have the default setup in I2B2, just because it's easy and everyone has these different data elements. But you can use the same methods in much more sophisticated ways. And it has been described in the papers, some of the ones that I cite in the PowerPoint here. Let's see. Is there any one or effort on supporting Postgres? That is a great question. One of the challenges here is that, again, it's very database heavy. We built this initially for Microsoft SQL Server. We had funding to have Prognosis company convert that SQL Server code to Oracle. We were looking for volunteers who may want to convert this to Postgres as well, but we're limited in resources on this. If someone does want to, is interested in that, I'm happy to work with them on doing this. Is there a comment there on that? Yeah. All right, so your institution may not be buying SQL Server or Oracle, but if you have a big LLM infrastructure, you can you can port it to your Postgres. That's really a good point, and we should see how that does. When we started doing this several years ago, we didn't really have that as an option, but that might be a good thing to test. We need a Postgres site who wants to try that out. Thank you.
Thank you very much, Griffin.